welcome back in the lab. So in the last video we discussed about these guys, the encoder. Try to make a zoom, and that we saw is these guys send two signals we call phases, and the two signals are 90 degrees from each other. And the concern with this type of signal is, for the decoding. It's a good thing that we are able to know in which direction the encoder is turning. But with the phase, we'll have some calculation, and if we increase the frequency, for example, if we put such a thing, on a motor, I'm not sure that we will be able to decode in a proper time. So that's why I decided to make a circuit that will make the decoding by itself. And when you use some simple circuit, it will do a great job, and it will not consume any kind of calculation on the computer, thing like that. So it remains for the machine the very best to do. So what I use, I'll show you here. The schematic. So it's a very basic schematic. So A and B are the two phases from the encoder. Here we are the first D flip-flop gate, and here is the second one. And at the output there is some NAND gate, So the purpose of this very simple circuit is to make the decoding. So in one way it will clock up. So if you turn counterclockwise, this output will generate a pulse train that's equal to the speed of the encoder. And if you change the direction, so if you turn in the other way, it will be the other output that will be activated. So most of the job will be made with those things, and it will help very much, for the machine to know how to use, the encoder. So with this circuit, the only thing that you have to do is to count the pulse in one direction and subtract the pulse from the other direction. So it's a very useful circuit, and also it can run, at very, very high frequency. So I guess that is able to go over a couple of megahertz. So it will be very helpful, even with a motor or thing like that. And I want to show you how does it work. And so I put a circuit here, on this prototype board. So there is the two single chip. The first one is a 4013, and the second one is a 4011. And there is a lot of wires. It's a little bit messy, but when you make some prototype, it's very easy. And the results could be seen, on the oscilloscope. So if I turn, on the clockwise direction, only one signal, is making, and the pulse train that you see is just following, the speed of the shaft. So the decoding is already made. And if I turn counterclockwise in the other direction, you can see that it's the other output that is running, and it let us show only the direction. So with this circuit, it will be very helpful, to decode these things. So it's more easy, and we do not need any calculation or thing like that. It's already done. So if you change the direction, it's the other output that activate. If you go back counterclockwise, it's the first one that is activated. So it's a very simple circuit, but very powerful. So we use this technique, you know, to use the encoder and to be able to gauge an axis very precisely. And it's one way that you can very easily, you know, check the position of an axis, and without consuming, you know, a lot of calculation or use some sophisticated things. So here it is, a simple circuit to make the encoder decoding, and it's quite useful. I have to think to find a way how to find, you know, the max frequency of this circuit, and maybe I will put a motor with a certain type of control to know, you know, what could be the limit of the circuit. But I guess that the limit also could be given through the datasheet of the, you know, of the two chips like I use here. So I will have a look at it and see what we can achieve as a max frequency for this kind of circuit. So the max frequency is something that is useful because if you want to check, you know, the RPM of a motor, you need to be sure that your circuit will be able to follow, you know, the speed of the system. So thanks for watching, and stay tuned.